Now let's learn about chemical properties of alkali metals. As I told you previously, alkali metals have a tendency to lose electrons. They enter into chemical reactions by losing electrons. So they act as good reducing agents. And we have already seen the order of reducing power. We said that the most powerful reducing agent among alkali metals is lithium, and the least powerful among them is sodium. So remember that they participate in chemical reactions by losing electrons, and in this way they act as good reducing agents, and the most powerful among them is lithium and the least powerful among them is sodium. Now under chemical properties, let us first learn how they react with components of air. You know very well there are two important components present in air. One is oxygen, the other one is nitrogen. Apart from that, you have carbon dioxide and noble gases. The very important components present in air are oxygen and nitrogen. Let's see how alkali metals react with these components of air. The general representation can be shown like this. M is an alkali metal. It reacts with oxygen of air and it gives an oxide M2O. And the reaction will not stop here. M2O then combines with moisture and get MOH, metal hydroxide. And again the reaction will not stop at this stage also. MOH then combines with carbon dioxide present in air. See, these are components of air: O2, H2O and CO2. Here I would like to tell you that this is a strong base and carbon dioxide is an acidic oxide. So this is an acid base reaction which takes place and you get M2CO3. It is a metal carbonate. So we can put it like this: when an alkali metal is exposed to air, it ultimately transforms itself into metal carbonate. During this process of transformation of metal into metal carbonate, there are three important reactions which take place. Number one is reaction with oxygen to give metal oxide. Then metal oxide reacts with moisture present in the air to give metal hydroxide. Metal hydroxide, being strong base, will react with acidic component present in the air, that is carbon dioxide, to give metal carbonate. You get a piece of metal carbonate. So if sodium is left out in moist air, you end up with sodium carbonate. Here I would like to add one more important point, that lithium has an ability to react with nitrogen as well to give Li3N. It is called as lithium nitride. We know very well nitrogen, because of presence of strong triple bond, is chemically inert. No alkali metal will react with nitrogen except lithium. Lithium is the only alkali metal which can directly combine with nitrogen and you get lithium nitride. So with sodium exposed to air, don't expect sodium nitride to form, but when lithium is exposed to air, you get a mixture of lithium oxide and lithium nitride. Lithium oxide may further undergo this type of reactions, but lithium nitride will stay there as Li3N. So the only alkali metal which can react with nitrogen directly is lithium. This can be explained on the basis of very small size of lithium and very high lattice energy of Li3N, which makes this reaction possible. So this is how alkali metals react with components of air. Let me put it once again. The alkali metal first reacts with oxygen of air to give oxide. This oxide dissolves in the moisture present in the air to give hydroxide. Hydroxide, being a strong base, will react with carbon dioxide and acidic oxide to give metal carbonate. And then an exceptional feature of lithium is capable of reacting with nitrogen of air to give Li3N. This is the only alkali metal which can directly combine with nitrogen. Remember, Na plus N2, no reaction. Potassium also, no reaction. Rubidium and cesium also do not combine with nitrogen directly. Now, let us move on to the next reaction. Just go through the reactions once again. M plus O2 gives M2O. You can balance this equation. You can put 4 here, this becomes 2, and then M2O reacts with water to give MOH, metal hydroxide. This is moisture which is present in the air. Then MOH will react with carbon dioxide. You can as well balance this reaction. 2 MOH plus CO2, that gives H2O. This is how the reactions take place. Li plus, this also you can balance, make it 6, then this becomes 2 Li3N, lithium nitride. Let us see how alkali metals react with pure oxygen. This time we are using pure oxygen. Reaction of alkali metals with pure oxygen. If you take lithium, it will react with oxygen and you get Li2O and Li2O2. This is a normal oxide, this is a peroxide, lithium peroxide. This is major and this is the minor product. So, we can say when lithium combines with oxygen, it gives a large amount of Li2O and a very small amount of Li2O2. Li2O is a normal oxide, Li2O2 is a peroxide. Sodium, on the other hand, reacts with oxygen. Here you get a mixture of two types of oxides, Na2O2 and NaO2. This is the peroxide and this is called superoxide. This is minor and this is major. So, you can put it like this: sodium reacts with oxygen to give sodium peroxide as a major product, and a minor product is sodium superoxide, NaO2. M plus O2, here M can be potassium, rubidium or cesium, any of these, the rest of the elements. They combine with oxygen to give superoxide. This is, as I told you, superoxide. So, we can put it like this: there are three possibilities. When alkali metal reacts with oxygen, you can think of three possible products. One is a normal oxide whose general formula is M2O, then you have peroxide whose general formula is M2O2, and superoxide whose general formula is MO2. This is MO2. KO2 can be called as potassium superoxide. Here what we need to remember is lithium forms mostly normal oxide and a small amount of peroxide. Sodium gives mostly peroxide and a small amount of superoxide, whereas all the other three elements, potassium, rubidium and cesium, give rise to superoxide as the major product, and they give very small amount of peroxide. The reason for this anomaly we will be discussing in the next section. For the time being, just remember that there are three possible products: normal oxide, peroxide and superoxide. Lithium mostly gives normal oxide, sodium mostly gives peroxide, and others mostly give superoxides. Others means potassium, rubidium and cesium. Now, why such a thing happens, we will be discussing in the next section under chemical properties of compounds. So, this is regarding reaction of alkali metals with oxygen. The various alkali metals react in a different manner. You can see the reactions here. Now, let us discuss reaction of alkali metals with water. This is a generalized equation I am writing. Alkali metal reacts with water and you get alkali metal hydroxide, and the gas produced is hydrogen. You can balance the equation like this. So, remember, a metal hydroxide is produced and hydrogen gas is given out. It is a vigorous reaction. Alkali metals react violently with water and the gas produced is hydrogen. and the solution becomes alkaline due to formation of metal hydroxide, which is generally a strong base, except in case of lithium. All other alkali metal hydroxides are strong bases. You will learn in the next section. So remember, alkali metals react vigorously with water and the gas produced is hydrogen. The solution becomes alkaline due to formation of metal hydroxide. Here one important point which is to be remembered is lithium least reactive. This is the most important point you are supposed to know about this reaction, that we expect, because lithium is the most powerful reducing agent, we expect lithium to react most readily with water, but on the contrary, lithium is the least reactive metal among alkali metals. When it comes to reaction with water, lithium is least reactive. The reason is strong metallic bond. See, if you put a piece of sodium on the surface of water, it will melt and it will spread on the surface of water and occupies. There is larger surface area of contact between sodium and water. This makes the reaction proceed fast. But when it comes to lithium, lithium has the highest melting point among all alkali metals, so it will not melt so easily and it will not occupy larger surface area immediately. So that makes the reaction of lithium less violent. It is less violent when compared to all other alkali metals. Lithium does not melt so readily and does not offer greater surface area for reaction with water. That is the reason. That's how they react with water. So remember, the solution becomes alkaline due to formation of metal hydroxide. The gas produced is hydrogen, and the metal which reacts least violently is lithium. It is due to its high melting point. Let's learn about reaction with hydrogen. Alkali metal reacts with hydrogen and you get a compound of this type, MH. This is called metal hydride. This is how you can balance the equation. This is called as metal hydride. This reaction takes place at elevated temperature. You need heating. So when alkali metal is heated in presence of hydrogen gas, you get a solid metal hydride. One important point you need to remember about alkali metal hydrides is they are all ionic hydrides. Alkali metal hydrides are ionic hydrides. And LiH is thermally most stable. LiH is thermally most stable among the hydrides of alkali metals. This can be due to high lattice energy. Due to its high lattice energy, LiH is thermally most stable among hydrides of alkali metals. All alkali metal hydrides are ionic. All alkali metals can combine directly with hydrogen on heating. And I told you, all alkali metals do not combine directly with nitrogen. Only lithium reacts directly with nitrogen to give lithium nitride. When it comes to reaction with hydrogen, all of them react with hydrogen on heating and you get alkali metal hydride, which is an ionic compound. So that's how they react with hydrogen gas. They react with hydrogen gas at elevated temperature. They give metal hydride, which is an ionic hydride. And among them, the thermally most stable hydride is lithium hydride, and it is due to high lattice energy. The high lattice energy of LiH is in turn due to very small size of Li plus and H minus. That's all about reaction with hydrogen. Let's learn reaction of alkali metals with halogens. This is a generalized equation. Alkali metal reacts with halogen. This is a solid. Halogens are generally, we use them in the form of gas. You get a metal halide which is solid. The reaction is vigorous reaction. It's a very, very vigorous reaction, and it becomes highly vigorous when the halogen is fluorine, and when the metal is cesium, the reactivity will be very high, because cesium has a great tendency to lose electron and halogen among halogens, fluorine has the highest tendency to gain electron. So, the reaction becomes most violent when the halogen is fluorine and when the alkali metal is cesium. There is no exception. All the alkali metals react with all the halogens and the type of compound formed is Mx. This is an ionic metal halide, alkali metal halide. All are ionic compounds. That's all about reaction with halogens. It's a very simple reaction. They react in this ratio and you get a Mx type of compound, 1:1 compound, Mx type of compound. They are predominantly ionic compounds. Let's not talk about how they react with liquid ammonia. Ammonia, you know, is a gas, but if you cool it and compress it at a temperature below -33 degrees Celsius, it exists as a liquid. So, when an alkali metal is mixed with liquid ammonia, what happens? Remember, alkali metal plus liquid ammonia. What you get is a deep blue colored solution. Once again, any alkali metal, when dissolved in liquid ammonia, you get a deep blue colored solution, deep blue colored solution. And remember, the solution is paramagnetic. The solution formed will be paramagnetic. And the solution acts as a good reducing agent. And another important feature of this solution is the solution behaves as a good electrical conductor. I'll repeat these points. When you dissolve alkali metal in liquid ammonia, you get a deep blue colored solution. This solution will be paramagnetic in nature, and this solution will act as a good reducing agent. You know Birch reduction in organic chemistry, where you can bring about 1,4 reduction of dienes, you can bring about reduction of alkynes, partial reduction of alkynes to trans alkenes. So, a solution of alkali metal in liquid ammonia behaves as a good reducing agent. Apart from that, the solution will behave as a good electrical conductor. So, these properties, color, reducing nature and conductivity, even paramagnetic nature, all these properties of this solution is attributed to the presence of what is called as solvated electrons. I will show you with the help of equation. So, please remember what are the properties of this solution. This solution is blue colored. That is the first thing you need to know. Alkali metal, whether it is lithium, sodium, potassium, rubidium or cesium, any alkali metal when dissolved in liquid ammonia, it is going to produce a deep blue colored solution. That is the first thing you need to know, is it gives a deep blue colored solution. The next thing is the solution will be paramagnetic. About magnetic nature, you should know that the solution is paramagnetic. Another important feature is this solution will act as a good reducing agent, can be used as a good reducing agent. Please remember that reducing agent is a species which can supply electrons, And then another important feature is this solution will act as a good electrical conductor. So, these 4 properties, color, conduction, paramagnetic nature and reducing nature, all these properties can be explained on the basis of this reaction which I am going to write now. All these properties are due to presence of electrons in the solution. So, I am going to put that equation here. Let us take a generalized example. This is M, alkali metal. I am putting L here indicating that it is a liquid ammonia. I am putting S here indicating that the metal is solid. When you mix these two, what you end up with is M becomes M plus. and ammonia, you know, is the polar molecule. So M plus will get solvated, it will get surrounded by ammonia molecules. You call it solvation. This is a solvated cation. Apart from this, you get E minus electron, which also gets solvated, surrounded by ammonia solvent molecules. So the solution of alkali metal in liquid ammonia is expected to contain solvated cations and solvated electrons. These two species are responsible for these properties. Solvated electrons are responsible for paramagnetic nature. Solvated electrons are responsible for reducing nature. And then these two species are responsible for carrying current. Apart from this, you can say the blue color of solution is a consequence of presence of solvated electrons in the solution. Here I would like to add one more point. If you go on adding more and more alkali metal in the liquid ammonia, then the solution develops bronze coloration. It from deep blue solution, it changes to bronze coloration when you increase concentration of alkali metal in the solution, and this solution becomes diamagnetic. The solution becomes diamagnetic. Up to moderate concentration, the solution will be deep blue colored. It will act as a good reducing agent, it will be an electrical conductor, and it will be paramagnetic. On increasing concentration, it becomes diamagnetic and the color changes to bronze coloration. Deep blue color. These are the 4 important properties of this solution. All these are explained on the basis of this assumption of presence of solvated cations and solvated electrons.